Welcome to the VLSI Physical Design demo. So let me introduce about myself. So I was Prasad. So I have a total 13 years of experience in VLSI Physical Design. So today we are going to discuss about the basic VLSI Physical Design flow. Okay. So I'll start with the ASIC flow. So basic ASIC flow. Then we'll discuss what is the VLSI Physical Design and for each stage what we will do. Right. So everything we'll discuss in detail in a given time frame. Okay. Okay. So, yeah. So first of all, right, like what is VLSI? So you might, if you are an BTech graduate, MTech graduate, you might have the, in academic also, you might have the subject, right, VLSI. So which is nothing but a very large scale integration. So what is that very large scale integration? So here it is a process. What we can do in this process, we will combine millions or billions of mask gates onto one chip. So if you take this is a chip, right? If you see this left one, right? So this left image, it is a chip after the package. Okay. So this is the layout view of the same chip. Okay. So as a physical design engineer, you can see this type of view.
The
Okay.
screen is
So
not
this is
visible. Your screen is not visible.
is
You
it?
can reshare. You can reshare the
Sure. Yeah. Yeah. Sorry for that, guys. So today what we are going to discuss, right? So we'll discuss about the VLSI physical design flow. So first, we will discuss what is ASIC flow. So what is the need of ASIC, and then we will discuss what is VLSI physical design. So what majorly we will do at VLSI physical design, and what are the different stages involved into the VLSI physical design. So end to end, we are going to discuss today. Okay. So first of all, what is VLSI? Right, so you might if you are a btech or mtech graduate, right, so many of you have done masters also, so you might aware of the what is VLSI. So it's a very large scale integration we can call. So here we started integrating the chip, right? So if you see early stages, we started integrating like a few hundreds of tens of hundreds, and then we can come into millions. Now we are integrating billions of mass transistors on a single chip. Okay, so this is the advancement in the industry, you might say. So when there is advancement in industry, you always expect the good uh, growth in a career wise also. So that's why nowadays you might see so VLSI is everywhere, right? So if you take a small any of gadget, any of electronic gadget, so now you might join through mobile phone or laptop, right? So in your mobile we have multiple SOCs. SOC is nothing but a system on chip, which is nothing but IC, we call integrated circuit. So this is the one example. You see the left image, which is I just marked it. So this is one IC. So after IC after package. So this is IC. Maybe other people normally see when you open your motherboard and all. So this is the layout view. The right side one is the layout view. So this is what, as a physical engineer, we have to develop this layout. Okay, so we'll discuss about the ASIC flow. So what is ASIC flow? So what is ASIC? It is application specified integrated circuit, right? For specific application, we are going to design our IC integrated circuit. So if I was working on a mobile phone, right? So for example, I was in a mobile manufacturer, right? So for mobile, so what I need one SOC or I need one chip, right? So I should have some specifications, correct? So the specification is I should have the specification. Okay, for this mobile I can use it is 5G. Okay, and its speed is 4 gigahertz, right? And it can consume some 3 volt, right? And the size also dimension, right? So I should be like 2 cross 2 So this is height and width. So these are my specification. So that is what we can get from the customer, right? So when we are working in the industry, so this is the very important step. So we have to understand the specification. So what SOC we are going to build and what are the specifications. So specification, for example, you can take it's the speed and the power requirement and the size. So these are some specifications. So according to the specification, so we have to go with the architecture, right? So we have different architectures, right? You might seeing that, you might aware of some discrete processor, right, and all, right? So and Blackwell. So recently we are using the Blackwell architecture as well for Tegra chips. Okay, so different architecture, we have to decide which architecture will work efficiently for our specifications. So once we have decided, so we'll go with the functional design and logic design. Okay, so here what majorly we will do, we will write the Verilog code. So whatever the, for example, the functionality, for every functionality we can start building the Verilog code or RTL code. So once the code is ready, we can see the we can convert that code into the circuit description language. Okay, so we, after that we can start the physical design. So when we start the physical design, these are the steps involved in the physical design. We'll discuss one by one in the coming slide. So after physical design, we have to sign off. Sign off means we have to check each and every metric of our SOC, right? So it will be timing, it will be area, it will be some DRCs and everything. So we have to verify. If it is verified properly, then only we go to the fabrication. So fabrication, nowadays, like mostly we will go to the TSMC and Samsung, depends on the our SOC, right? So once the fabrication is done, so we have to do packaging and testing. So before packaging, testing is very important. So without testing, if I can deliver my chip, right, to the customer, so what they will do, they will take the chip, then they will integrate into the SOC, right? So once they integrate, after that, if it is the chip is not working, then it is waste of use, right? So we can waste completely the money of the customer and also the time, valuable time as well. So that is why the testing is very important. So once the testing is package is done, then our chip will be ready. Okay, so this is what the complete ASIC flow. So now in this discussion, in this session, so we are going to discuss about the physical design. Okay, so physical design will start from partitioning. Okay, first we have to take our SOC, okay, our IC. So we have to divide into some partitions, then we can start a floor planning. Okay, so in floor planning, what we can do, we can do the macro placement. So once the macro placement is done, and we can do the power planning. So once we are good in macro placement and power planning, then we can start the placement. So after, we'll go with the CTS and the routing. Finally, once the routing is done, if we have all DRCs and everything was clean, then we can go for the timing closure. So these are the steps involved from here to here. So in the physical design, so once my timing and DRC was clean, so I'll go to the here again, the physical verification, which is majorly concentrated on DRC and the sign off. Sign off means IR sign off. Okay, we have different sign offs, IR formality, right? So everything should be passed. So then only we will go to the fabrication. If anything went wrong, so we can come back. Okay, for example, if I have any DRCs, let's figure out at this location, so I can come back at signal routing, I can fix it, and I can proceed to the sign off. So in sign off, all my metrics should be clean. I cannot sign off without any without cleaning any single violation, even it is timing, even it is IR, even it is EM, even it is DRC as well. Okay, so yeah, so hope you understand what is ASIC. So today main topic was physical design. So yeah, okay. Um, Please, if you are not talking, like please mute at your end. Okay, so as I told, so in a physical design, so we'll start at the partitioning. So sometimes PD engineer can do partitioning. Okay, so most of the time we have separate team for the partitioning, so they will completely take care of the partitioning. Okay, so our job will start from the floor planning. So before floor plan, what we can do, we can load the design. So once we load the design, we have to do floor planning. Okay, so what is for planning? So, and what is the power planning? And what is the placement? What is CTS? And what is routing? So what is this timing, power, and what is this sign off and all? So each and every one we will discuss in detail in this today's session. So first of all, I'll just give the brief introduction. So in the floor plan, what measure we will do? We will place the macros. So macros are nothing but it's a kind of IP. Okay, so in your desktop system, volume desktop system, you might seeing, right? So if you want to increase the speed, you can insert the RAM, you can buy the RAM from the market and you can insert the RAM. So it was not inbuilt, right? So you can insert. Similarly here also we can buy IPs, right? IPs have some specific functionality, so we can IPs from other customer and I can insert it in my SOC, and after I can do the power planning. So the major requirement of my power planning is I have to supply power to the each and every corner of my SOC. Okay, so then I can go for the placement of the standard cell. Okay, standard cell is nothing but our AND gate, OR gate, right? Our flops, right? So this we call as a standard cells. Okay, so those standard cells we have to place inside the given boundary. So then once it is done, we have to go for the CTS. CTS is nothing but clock tree synthesis. Here we have the sequential elements, right? We have the mux, we have the flop, and other sequential elements also. So if you see your circuit design, okay, your digital design, for each flop we should supply the clock, right? So that is what we will do at CTS. We will build a clock for the all sequential elements in the design. Okay, once it is done, then we'll go to the routing. Routing is majorly concentrate on DRC fixes and the physical connection between two pins. Okay, in Verilog code, what we are writing, okay, this AND gate, okay, I have an AND gate here, all right? So this AND gate output can go here and I can connect to here. So this is the logical connectivity we might writing in the Verilog code. But in routing, it will physically route with the help of metal layers. Okay, so with the help of metal layers, it will route. So there is not only one single gate, right? As we discussed in the VLSI, so we are integrating millions of gate, right? So 1 million, just assume, okay? So it is almost like a 10 lakh, right? So 10 lakh cells I was integrating on my one chip. So 10 lakh cells means, for example, 10 lakh gates. It will be flop, it will be mux, it will be AND gate, it will be OR gate. So these gate have multiple pins, right? So you can take 3 cross 1 AND gate, which should have 3 input and 1 output, right? So you can take a 4 class 1 OR gate, it should have 4 input and 1 output. So 4 input means 4 input pins. For each pin, to make the connectivity, we need the routing precursors, right? So in lower technologies nowadays, so routing is very critical. So we should do routing, okay, without any DRCs. Okay. So these steps like from placement, CTS and all. So parallelly, we can check the timing and power analysis. So why timing is important? So in your academic, you might seeing, right? So setup time, hold time, and all. So the same requirement will be we need to meet it here. So if we not met those, okay, so we don't achieve the required speed. So because in this first slide we have discussed it, right? So my specification was 4 GHz. Okay, so if I want to met the 4 GHz, I have some frequency, right? So that frequency I have to meet, otherwise it is no use, right? So I was trying with 4 GHz. I was working on an Intel. Okay, so I was working with 4 GHz. If I not achieve this frequency, some other competitor, AMD, so they will come and they will release the chip with 4 GHz. So that's why it is always very important. So as a physical design engineer, you should always concentrate on PPA. Okay, so which is power, performance and area. Power, we should utilize as less much power as like, so for example, I was using the one SOC in my mobile. Okay, so if I was the chip consuming more power, what will be effect on my battery? It will drain up easily, right? So instead of 5 hours, it will dry up in 1 hour. So for every hour I need to charge my mobile. So those type of mobiles you won't buy, right? We won't buy, definitely. So then there will be no market for those kind of chips. So that's why the power is very important. And other is the timing. Okay, so timing means we should always see the speed. Okay, for example, you are doing some calculation. Just example, you have entered 2 plus 3. Okay, you know what is that output? Like if it come after 1 minute, you will prefer those kind of mobiles, right? It will be very slow. And if you want to use it for gaming purpose, right? If it is not effective, you cannot buy those type of mobiles, right? So if you not buy those type of mobiles, then there will be more no market for those particular chip, right? So that's why the performance also came into picture, and the area. So if you seen in your day by day life, so every year we can see there is a shrinking in the devices. Earlier, if you see, your mobile size was somewhat different. So now you see it was different. So earlier we are using the desktop, now we are using the laptop. Okay. So area is reducing. So that is a major key role for the area. So we have to fill all our cells in a given area, okay, by meeting my performance power requirement. So this is the challenge for the physical design engineer. So always we need to keep in mind PPA, power performance area. Okay. So once routing is done, okay, our PPA targets are should be controlled, and then we go for the DFM, okay, design for manufacturability. So here, any related manufacturer related checks, right? It will be power and ground shots. So those we can check, and then we can go for the sign off. So this complete bottom will comes under sign off. So it is a timing sign off. That means whatever the achievable frequency target we have put, right? So for gauges, if my timing is clean for the given time period, so I can achieve the four whatever the four gauges, right, we have decided in our specification, that I can achieve. And similarly the physical verification. So in a physical verification, what majorly will comes, it will comes to the DRCs. Okay. So there is some rules we'll get from the foundry, okay, which is like from this metal layer to this metal layer we should have this much spacing. Okay. So that kind of rules will be there in a come from the foundry, so that we have to follow. Okay. So that comes under physical verification. And the formal verification, which is very important. So it will be, it will check so what you are doing. So input you are getting, okay, here you are getting input. What is the input? Your verilog code. Okay. So after routing or after all these steps, you should have the one more verilog. So you can compare this verilog versus this verilog. So when you compare those verilog codes, okay, the functionality is same. So by mistakenly if you add one inverter, what will be happen? Your formality verification is going to fail. So then you have to go back and you have debug. So what
अभी
what when
पूरा पूरे मतलब नई नई कंपनियां बहुत हो गई हाँ अपन
uh, uh, yeah, please
continue. I will remove the person. Don't worry, I will remove this person. Hmm.
yeah, sorry.
Yeah, now it is.
Okay.
Please
So
continue now.
yeah, so my screen is visible, right?
Yes, yes.
Oh, okay. So what we can take in a formality, we will take two netlist. One is a input netlist, which is a golden netlist, and we can take the revised netlist. That is after physical design, we'll get one netlist. Okay. So these two netlists we can compare, and then we can see unmatched points. Okay. Unmatched points. Our unmatched point should be 0. Then only we can, our formality is passing. So if all this passing, then we will generate a file called GDSII file, okay, which is a graphical representation of all our layout. So this file will send to the foundry. So then they will start the fabrication process. So this is how the basic physical design flow. So now we have discussed it, right? So there is a step called partitioning, floor planning, placement. So we'll see what is the partitioning, what is the floor plan, what is the power plan. We'll see one by one, and then we'll see what is the sign off. Okay. So coming to the partitioning. So what is the need of partitioning? The first thing, right? So just physical design understanding is very easy if you map it to the real world. Okay. So this partitioning. So what it will be? We have to see this is my circuit. Okay. This is my complete circuit. So if as an engineer I want to build, I want to completely do PNR for this. It is very difficult. So PNR we nothing but place and route. Okay. So if I want to do for planning, placement, and all for this complete design, it is very difficult. So what I can do, I can divide these complete chips into small blocks. You see, so this is a block A, and this is a block B, and this is a block C. So I have cut in this fashion. Okay, so this is mainly to separate the like functional block. Okay, and also make our placement and routing means the PNR easy, right? So what I can do, if I want to, instead of see, I have this complete big design. Okay, so this design have 3 million. Okay, so 3 million inst count this design is having. So if I want to start PNR for this, if I want to do complete floor plan to routing to this design, it is somewhat difficult. Runtimes itself is very high. My placement will take 4 days. So instead of that, what I can do, I can divide this complete 3 million inst count design into 3 portions. Like here 1 million, and here 1 million, here 1 million. It won't be exact like 1 million. Sometimes you can see here you can use the 0.5 million, and here you can use 1.5 million, and here you can use 0.1 million. So this is also fine. So in this fashion we will do. So we cannot blindly do the partitioning. Okay, there are so many cost factors involved. So one factor is the functionality. Okay, so other factor is the wire length, right? So everything we have to check. So then we can do the partitioning. So once the partition is done, so we can get the dimensions of this our B box. So then we can start the our PNR. So before starting PNR, we should understand what are the inputs needed for the PD. Okay, and also discuss. So this partitioning is of 3 types. One is aborted and non-aborted and mixed. So see, if you see this completely this one, right? So this is my one chip. Okay, so we can call it as a full chip. So this is a one type of partitioning. See here I was divided. This is a block 1, block 2, block 3, block 4, block 5, block 6. Okay. So here one block, other block I aborted. That means there is no channel space between these two blocks. Okay. In the case 2, I have given a channel. So it depends. Okay. So it depends on the which SOC you are working. Okay. And it depends on your engineer. Like see, if I was doing, I'll go with, I was in my recent designs, I went to the this mixed one. Okay, in some locations, because if there is some glue logic, okay, so the logic which cannot belong to 1 and 2, what I can do, I can place here. So in this case I can go with the non-aborted partitioning, right? So if I want to, for example, I have some glue logic. Okay, so glue logic is nothing but the spare logic which is not belongs to any block. Okay, any block in the given part blocks only. So I have some module. So I don't want to place it a module 3 and module 4. I want to place between these two. So what I can do, I can give some channel here. I can place all this here, and I can make the connectivity. So that's how we have to decide. So these are you need to understand that these are very important. Okay, so nowadays, so majorly we are going with so this and this. Okay, so this is the high priority. So most of the uh, GPUs and CPUs, they are using this and this also. Okay, so in this case, what we have observed, right, we are wasting so much area sometimes. See, right? So instead of that, I can go with the mixed, right? In, for example, here I don't want to give any space, right? So here I aborted those two. Here I want some space here and here. So then I can give here space, right? So here I don't want to give any space. So I just aborted here. So this mixed one helping into improve the area. So as I told, what is our target? PPA. So if you do proper partitioning, you will get benefit in area, right? So for everything, you should have this PPA in mind. Okay, chalo. So now we'll discuss what are the basic inputs for the physical design. Okay, so the very first input is the technology file. Okay, the extension is .tf. Okay, so this file we will get from the foundry. So foundry is nothing but TSMC I was taking in this case, or you can take the Samsung also. It depends on which foundry you are working. And then gate level netlist. So gate level netlist is nothing but your Verilog code .vg. So this code, who will write this code? So RTL guy will return, RTL team, they will write the Verilog code, and they will give the this .vg file. Okay, So there are different extensions will be there. Sometimes we can see only .v also, okay, and sometimes you can see .sv, that is in system verilog, okay. And the constraints is very important. So as I was continuously speaking about the PPA, speed and all, right? So I have to put somewhere what is my target speed, right? So here we will decide with the help of clock, okay. So the clock frequency we have to give. So that clock frequency will put in a SDC file, .sdc, okay, which is design constraint file. So this will get from the designer, okay. So if you are a designer, you can decide, okay. So majorly we need to discuss with the specification team, understand what are the requirements. Accordingly we'll go with the constraint development, okay. So in the SDC we have the create clock, okay, input delays and output delays. So even we will estimate the delays also. And the very important one is the logical and physical libraries, okay. So that is nothing but .lib and .left. So for example, in a Verilog code, I just defined an AND gate. Okay. Yes. Okay. I was defining an, okay. I was defining an AND gate. So in a Verilog code, so I want to understand, so what is the delay, right? I need to understand what is the delay from A, B, C. So there is some delay, right, from A to C, and there is a delay from B to C also. So those timing information. So not only for the AND gate I was taking, you can take flop, you can take any net. So those timing related information will be there in the .lib. Okay. So which is timing information. So similarly, so we are talking about the area. So see, physical design comes now. So we have to discuss about the physical formation of the cells also. So for example, I have an AND gate. So I don't know what is the AND gate height and width. So in this left file, we should have the dimensions. Okay, what is the height? We can see like this only. Just this kind of box we will see. Okay, as an AND gate. So what is the height and what is the width and what is the pin? Okay, how many pins are there? For each pin, what is the different metal layer? So those information will be there in the left, which is nothing but a physical information. That's why we are calling it as the physical libraries. Okay, and coming to the def. So def is nothing but design exchange format. Okay, so which is nothing but design exchange format. So which is very important. So here, so we have did some partitioning. Okay, so I was a design engineer, so I did block 2. Okay, so I want to give this block 2 to some guy. So I have to tell to that guy, this block height is this much, okay, and width is this much, right? And there is a ports, right? So there is a communication from block 1 to 2. So there is some ports here, and similarly there is some ports here. Okay, so similarly there is some ports here. So this height, or you can say dimension, and port information, so we can pass with the help of def to the designer. Okay, and then we will also have the scan def. So we'll get this scan def from the DFT team, so design for testability. So after fabrication we have to test and then package, right? So if we want to test, we should have some testability logic. So for that we will insert the scan def. So scan def is contains the flops. Okay, so this type of flops it contains, such flop chain it contains. It will be like this, like this, like this. So what we will do after fabrication, so we'll send one pattern 1010. Okay, so output also we can expect 1010. If we are not getting the desired output, we can consider something is failure in the our chip. For example, if there is a connection, physical connection is not there here, so I won't get any output, right? So then I can say this is failed one, chip failure, okay, because of the break net. So similarly I should have the UPF also. UPF is nothing but unified power format. For example, if this is my block, okay, so in this block, so I was in this location I need 0.5 volt. So in this location I need 0.8 volt. So this is how the, if there is a multi voltage, right? So we can use UPF, we can tell to tool that So you use in this location, you can use 0.5. So in this you can use 0.8. So all the cells and respective macros we can place it here. And other input file is a TLU plus file. So it is a table lookup file which contains RC information. So you know what is RC, right? So which is resistance and cap. So which is directly depends on your delays. Okay. So these are the major input files. Okay. So which is needed for the physical design. So we have to load this inputs. So that step we call as the import design. So then only we can go for the floor plan. Okay. So we have to load this input, give this input. Okay. That step we call as the import design. Okay. Our initial design, and then we have to check validate all the inputs. Okay, well, we have to validate all the inputs. Then if all the inputs are validated successfully, if there is no issues, for example, if I have wrongly picked physical libraries, right? So I can see there is some errors in this validation. So again I can go back here and I can load the proper lips or lefts. Then I can again validate. So if it is fine, then I can go with the floor plan. Okay, we'll see what is floor plan in the next slide. Okay. Hello. So, so floor plan. So, which is a very first step we have to do manually. So, it is a very important step in the physical design. So, what is the floor planning? So, basic question, right? So, it is nothing but we have to place the macros. Okay, few people will call blocks, few people will call IPs. If you see this image, so this is the tool. Okay, this is IC compiler tool. Okay, image. We have the different tools used in design. So one we can use in our tool also, and we can also use IC compiler. Okay, so nowadays both are using widely, and both the tools are similar. Okay, if you learn one, other tool will automatically the similar way. So only the interface will be different. That's it. So if you see this, so this is my block height. Okay, so here to here, so this is my block height, and this is my block width. So this information I'll get from the def file, and these are the whatever these, right, this and all my macros. So when it comes to the floor plan, I have to place all these macros inside my core area. Okay, and these are the ports. You see this, right? So this dots, right, you can see. So these are the ports. Okay, and these are the macros or IPs. So in between we can see it is an empty space which is reserved for the standard cells. So you see here we have some in this location you have some in a violet color, you can see small dots, right? So these are the standard cell at floor plan stage. So this cell will sit outside only. Okay, at placement it will come inside, it will utilize this area. So that's why we are reserving this area. Okay, and also we will explain like different, what is the difference between what is the toolbar, what is the menu bar, right, and what are the settings. So we will explain all these settings. So with the help of these settings, you are going to place the all the macros. Okay, so nothing, floor plan is nothing but placing the macros inside the core area. Okay, or chip area you can take. So whenever you are placing, so there is some goals. Sure. So we are discussing about the floor plan. So floor plan is nothing but, so we have to place all the macros inside the core area. So see, whenever I was telling the place inside, so blindly we cannot place, right? So there are some guidelines and there are some objectives and targets. So as putting all targets into our mind, we have to place. The first target or goal is we have to minimize the area. Okay, how I can minimize the area? For example, this is a one macro. So it is, I have ports here. Okay, if I place this macro here, so it has to connect to here, right? So there is lot of wire length in between, it will add some buffers, multiple buffers. So it is not right way. So whenever there is a communication, I have to place it nearer. So that is the one thing I have to take care. Okay, and the same thing, if there is a distance, it will be more. So my timing is also very important, and also the wire length. Okay, and when yeah, thanks for meeting them. And see, if you do proper floor plan, our routing will be easy. Okay, it's like cakewalk for us. So we don't put much efforts at routing stage. Okay, which comes after 7 to 8 days of the floor plan, right? So if you figure out any issue again, you need to come back to the floor plan again, you need to do the steps, right? and then IR drop. So IR drop is very important in the latest SOCs. Okay, if you not do proper IR analysis and fix IR drop, so what will be happen? You cannot using your mobile, but your battery will drain out easily. Okay, so these goals are very important. We have to keep in mind. One is the minimizing the area, time, wire length, and routing easy and IR drop. Okay, so then come to the power plan. Okay, so once the floor planning is done, we can insert some physical cells, then we will go to the power plan. So the major objective of the power plan is we have to supply power to every macro, standard cell, and all the other cells present in our design. If you see, this is the some image of power plant. Okay, so you will we have the voltage regulator. Some voltage regulator will get to the power pads, and power pad to rings, and rings to rails. From rails to standard cells or macros will get the power. So this is how the power supply will be there in a physical design layout. Okay, and so coming to the placement. So what is the placement? So in an earlier floor plan you have seen, right? So all cells are outside. See, these are the standard cells for sitting outside. So when it comes to the placement, okay, so it's the process of placing the all standard cells inside the core boundary in an optimal location. So optimal location is nothing but, see, if you see this image, so these are the macros. Okay, so and these are the macros, and these are the macros. So this is colored based on hierarchy. So this R belongs to one module, and this R belongs to one module. This belongs to one module, and this belongs to one module. So whatever this module, right, all standard cells can sit near to this module only for better PPA. Okay, so tool will try to do in such a way that it will try to minimize the congestion and try to give the best timing. Okay, so accordingly tool will place the standard cells. So this is the basic placement flow. So first we have to do setup, design setup, and then if there is a scan chain, right? So earlier we have discussed, right, we are going to insert the scan chain, which is helpful for testing purpose. So we can detach the scan chain. That means we can remove the scan chain because scan reordering will happen at play stage. Okay, so then we can give some options. Okay, for example, if my design is timing critical, so all timing related tool options I can put effort high, then I will go with the placement, auto place, and nothing but the placement. So here everything we can control with the help of commands. So once the placement is done, I'll check the congestion and timing. If the congestion is not okay, I'll go back, I'll do some proper changes in my design. Okay, again I can do all this step. If congestion is passing, then I can go with the timing. So if timing is fine, then I can go and perform the CTS. If not, I will do additional optimization. Okay, so then again I'll go back to the timing check, and if it is okay, then I'll perform the CTS. So this is how the placement flow will be. Okay, so now we'll move to the CTS. So CTS, so as I told, right, we have multiple flops in our design. So for each flop we have to distribute the clock. So the main objective of the CTS is the clock distribution, right? So if you see this image, okay, so here before CTS this image. So at the CTS what we are doing, we are distributing the clock with the help of inverters and buffers. So why inverters and buffers? We have to, there are two goals for us, okay, in CTS. So one is the skew and other is the latency. So this skew and latency should be minimum. So that is our target. Okay, so the same one. So inside design you can see like this. Okay, these are the flops. So before CTS it will be like this. So after CTS you can see buffers was inserted, right? So to minimize the skew and insertion delay. And these are the types of CTS. So the first one is a basic clock tree. So this is clock source. Okay, it will divide by 2, and again it will divide by 2. Ultimately these are the flops. These yellow ones are the flops. It will supply the clock in this fashion. And similarly this is a different structure, clock mesh. Okay, so you can see this is the mesh structure. So there are some advantages, and this is the H tree. So since we are following this H tree, we are calling it the H tree structure. So how we will decide? Okay, based on our requirement. Okay, so I will tell one requirement due to interest of time. I don't want to go in detail. So I will, my requirement is power. Okay, as per experience I know H3 will give less power. Okay, will consume less power. Okay, so for power design, power hungry designs, I'll prefer the H3. For high speed designs, okay, so I'll go with the clock mesh. So according to the specification, we can decide. Okay. And then routing. So routing is a very important step in a latest VLSI physical advanced nodes. So this is the different metal, this is a different metal, this is a different metal here. You can take this is M1 and this is the M2, this is the M3, right? So we have to make the physical connection between these two pins, right? So I told right earlier. So I have the two, this is the one pin, this is the output pin, and this is the input pin. There is a logical connection. We have to make physical connection at routing stage. And types of routing, we have the power net, clock net, signal net, and critical nets like analog nets. Okay, analog nets also will be there. Those are critical. So all these type of routings will be there. We have to make the physical connections. Okay, and how the routing process will be there. So first it will do global routing, and then it will go for the track assignment, and then it will do detailed routing and search and repair. Global routing, what it will do, it will just estimate. Okay, here I have one pin and here I have other pin, or here I have one pin and here I have some other pin. So there should be a connection. Okay, this is the Manhattan distance. There is the shortest distance. You can connect from here to here. So that is what global routing will do. In track assignment, it will assign some track. Okay, here to here you can do, but you can use M2 metal layer. So that is what it will do. And the detailed routing. So based on the track assignment, it will route like this. Okay, so this is M2 here, and here it is use M1, and here M1, like that it will use. Okay, in between it will add one via here, it will add another via here. So that's how. And search and repair. So whenever it is doing like this, so there will be a shorts and opens, because if one net touch with other net on same metal layer, we can see the shorts and right. So if there is no proper, for example, if this net is breaking here, so then we can see break, right? So if we are not following the DRC rules, so that is also comes under DRC, right? So if you're not giving the proper spacing, so everything will taken care by search and repair. It will go there, it will see, okay, here I was seeing the shot. Instead of going like this, you can route in this fashion. Okay, here there is open, you can reroute this net. So that is what the search and repair will do. Okay, so this is what about the routing. And very important thing, the sign off checks. So till here we call it as a PNR. Okay, place and route. So once this is done, we will do formality check, LVS, layout versus schematic, and the DRCs, timing analysis, and DRVs like maxtran and maxcap. Okay, so we can do all these analysis. Okay, we have to fix all this, and then we go for the IR drop analysis and fixing. Okay, so if all these are clean, so formality clean, okay, LVS clean, DRC 0 are clean, timing met, and DRV clean. Okay, IR drop analysis fixes, there is no IR issues, clean. So then we will generate the GDS2 file and we'll send it to the foundry. Okay, for each formality there is separate formality team will be there. Okay, so for IR drop team will be there. For this LVS and DRC we will only fix, and timing also will only, timing and DRC also will only fix as a PNR engineer. Okay, so these are the sign off checks. So once the sign off check is done, so it will go to the fabric foundry. It will do fabrication, wafer preparation, and all the steps it will perform, and then it will come out and we'll test and we'll pack it, and then we'll send to the customer. Okay, so yeah, so I'll open for the questions now. Let's
Yes, sir.
see any.
I will ask you. Hmm.
Yeah,
Yeah.
open
So,
for
any
the
questions?
questions.
As
Yeah.
so any questions are there?
Yeah.
Yeah,
Yeah,
Turja.
please.
I said, yeah. So actually, I have a question. After CTS, if core utilization increases, then how to fix these types of problems, sir?
Okay, so after CTS, you are telling you have
Yeah,
your
after
utilization was
CTS, if
increased,
core utilization is high, yeah.
right? So because why it will increase, we are adding some buffers and all, right? So for example,
Okay,
I was it is increasing. Okay, so I have to check, so why it is increasing. So there are two goals, right, for us: skew and latency,
correct.
right? So for example, if you see this image, okay, so one cell is sitting here, okay, other cell is sitting here. So if there is always might trying to balance the skew, okay, that's why it is unnecessarily adding so many buffers here. It will trying to balance skew between this 1 and 2. Okay, so here what is the skew? So difference delays between from here to here to here to here. Okay, so
Yes, sir.
what we can do, we will just check. So what is the why it is adding so many buffers? So we have some methods, okay, so which call skew grouping. Okay, so that is the one thing, and we can also see exceptions. CTS exceptions will be there. Okay, so before that so we have to, in the placement flow I had told, right? So timing is okay or not. If timing is not okay, we cannot go to the CTS. If timing is bad, obviously you can expect some unwanted buffering at CTS. So if timing is good, everything is good, then you can control at CTS. Okay, you can give some exceptions, and you can give the skew grouping. So accordingly you can reduce the this also. Okay, also the other reason, no, why you can see more utilization, the selection of the cells. Okay, so what people will do, they might you might using the buffers. Okay, buffer inside is having two inverters. So instead of using buffer, I can use the inverter pair. So in that fashion also I can reduce the util. Okay.
Sir, if we use inverter, so it will occupy more area, right? Because the size of the inverter pair will be high, right?
See, for example, here I have A and here I have B. Okay, so
Hmm.
here instead of I was using the buffers right here. Okay,
Okay.
so I might using some 3 buffers or something like that. So instead of this, I can use a inverter pair only, one inverter here and other inverter
Hmm.
here. So like
Hmm.
that it will be helpful. So inverter pair inside the buffer also, we should have the inverter pair and the drive strength also, very important.
Okay. Thank
Yeah,
you,
good
sir.
question. Yeah,
Uh,
good question.
Sir, I have a question that I heard from my couple of friends that scripting is used majorly in physical design. So I just wanted to
Right.
know how is scripting really used?
For example, see, just now I had told, right? So A, B here. For example, here I want to add 10 cells. If I want to do it manually, I need to go this location. I need to do some steps will be there. Okay. We have to do create cell. Okay. Insert cell, add buffer on route. Two commands will be there. I have to go here and put one cell like this. Manually, it will take 1 hour. If I was have some scripts, I can add the scripts in single shot, right?
So my follow-up question is,
Mhm.
do we have any specific language which we need for this, or it's just like general Python or for like different
No, we will
languages?
use
It's
tickle,
just tickle, right?
rest tickle. Yeah.
Okay.
So it is very easy. Yeah, actually, I don't know like people aware of it, but tickle is very easy. When you compare to other languages, right? Tickle is very user friendly. There is not even much a difficult command also. It's very easy. Okay, if you at least if someone knows some small basics also, they can learn tickle easy. Any questions?
Yeah, sir. Another question, sir.
Yeah, please.
May I ask you?
Sorry.
Hello.
Yeah. Yes.
Yeah. Yes. Actually, for during CTS, we do CTS for reducing the skew, right?
Hmm. Right.
But sir, after clock synthesis, sometimes we need to increase the skew to reduce this whole variation. So
Right.
actually, I have a confusion then why we are doing this.
See, there are different types of skew, right? So one is a global skew
Huh.
and the other is a local skew.
Okay.
Okay. So you might controlling the local skew, not the global skew. So global skew, when people see initially when people talk about the skew, so they might talking the global skew, but
Okay.
you are you are controlling the local skew, so it won't impact your total skew. Sometimes you will increase the local skew, it is okay, it's fine. You can fix the violation. So it won't impact the design, right? Only the path only. For example, in the same location here, you might I need to add some 2 cells here, right, to fix my
Okay.
violation, or I can add 2 cells here to fix my whole violation. So it will impact do some changes in my skew and insertion delay. So which is okay. Ultimately, we have to take care of the power and timing also. Not only that's the major targets, okay? So
PPA.
skew, latency, but power and timing also will be there. Okay, since it is not a detailed CTS class, right? So I was not told those. Okay, so always if you see, even though you are violating the skew, for example, your skew might be like plus 25 PS. So if you make it to plus 20, your hole will fix, right? Okay,
Okay.
at the time you can make it. It is fine. No issue on that. So your timing and power is high priority. So why people are going with the low skew and minimum insertion delay, right? So they will achieve good power number and timing. So that's why the targets was set like that. Yeah, good question. So is it you got some idea?
Yes, sir. Yes, sir. Thank you,
Okay,
sir.
great.
Yeah. Thank you, sir.
Yeah, good. Any other questions? Please mute at your end, so it will be helpful for others. No, others. Else I can mute. Yeah. Thanks, Ashutosh. Thanks for the compliment.
Any other
Yes.
queries?
Sir, here we use buffers, right, sir? In the second.
Right. Yes. Oh, sorry. Hello.
Excuse me, sir.
Yeah. I was able to hear you. Yes.
Yeah, I just want to know, like, we do have the magnet placement and the course placement. So can
At the
you,
placement.
magnet placement. So what exactly is the magnet placement in
See,
the placement state?
right. See, for example, whenever you talk about the magnet placement, right, we will use for the fixed object. Okay. Right. So what are the fixed object? Generally, ports and macros.
Macros,
Okay,
yeah.
for example, if you see, let's take one example. Okay, from here only. Okay, so this is one logic. Okay, you see the color, na pink color. So this logic is talking to this macro. Okay, so since it is sitting from so far, I might see the timing violations. Okay, I want to pull this near to this macro, right? So what I can do, magnet placement, I can give this macro name, and I can this macro name as an object. Okay, and I can give the cells, and I can give all list of cells. So when I do place again, so this cell will sit here. Okay, so that's how I can improve the timing. Okay, and what is the other question, by the way? The course placement, right?
Yeah.
Okay, so before magnet placement, what tool will do? The course placement is nothing. Okay, it will just place cells from outside to inside. It won't bother about the legalization and all. Okay, there will be a cell overlap. Okay, there will be a, some for example, you might know, right? So cell should be on properly. For example, these are the rows. Okay,
Yes, legalization. Yes, sir.
you know, okay, cell, ideally cell should sit like this. Okay, then only should have proper VDD and VSS. So if cell is sitting like this, it is an illegal location. So course placement won't bother about it. Responsibility is just take it and put it inside. Okay, so just relate our PD to general things. So might be, you might see that some industrial processing, right? Everyone cannot design this complete build the mobile. Someone will insert the display, someone will add the battery, right? So the course placement job is just to place the cell inside. Okay, that's it. So then we have the next step called legalization. So there it will take care of all legalizations. And you got the answer, or you need some?
Yes, I got it, sir.
I would appreciate really. Any other
Do we
question?
have any other doubt? Anyone on any other doubt?
So you can feel free, okay? It's not like you cannot ask questions.
Sir, if we do this magnet placement, so we might have get this condition, right? Because it will pull all these standard cells
Right.
in one location. So
See, there will be chances, okay? There will be chances. So if there is a congestion was coming, again, what we can do, we have to fix it incrementally. So that's why the placement is not one day we can do. It's a iterative process, right? So you see in the flow also. So once I done the magnet placement, na, so what I can do in see these options here, I can give the magnet placement command, right? So I'll do the placement again. What I need to do, I need to check the congestion, right? If the congestion is came again, I can go back. Instead of this location, I can add the blockages, partial blockage, right? Or I can add the padding also. I think you might know what is padding, right?
yes, sir. Yes.
Okay. So that we can do. So it depends on the particular location, right? So for example, if I was getting only for the cells, I can go for the padding. Okay. If I was getting in the location, I can go for the partial blockage addition.
Okay.
Good follow-up question. Any other?
Any other
Sir,
query? Any other questions?
so can AI replace the physical design, sir?
No, because see what AI will do. So AI can do the macro placement, but it won't analyze this PPA targets, right? Okay, there is no possibility as of now. Maybe after 10 years there will be chances. Okay, in between 10 years it won't, because see this physical design engineer like human itself not able to understand sometimes how tool is placing. Okay, so then AI will cannot understand, because for AI we have to guide, right, initially. So you might think whatever the answers you might think. For example, you might just tell in AI you can do what is the physical design, sorry, what is the placement. What it will do, it will just give some text, right? So how it will get, it will get from other source, right? So we have to feed all this information, then only it will do the. So at least 10 years it will take, okay, if you want to feed all this information to the AI. But it won't completely. So few things we can expect. The macro placement, yeah, soon it will replace, but other things, right, analysis thing, it won't. Okay, and see what will be happen, right? The major drawback in AI, decision making. It cannot make the decision, right? So this is PPA, right? So it, see my PPA, for example, I was working on a high speed computer. So my performance is important, right? So when compared to power and area, sorry, power also important, but just assume it is on a desktop, not laptop. So my performance is important. So I can make a decision, but AI cannot make the decisions, right? You agree on that point?
Yes, sir.
It won't take the decision, but I can take the decision. I can give some high priority to the this one, or I can contact the customer or client. I can discuss with him, okay, so what is your priority, tell me. Power is your priority and performance is your priority. So those type of discussions, and we have to be done in the physical design. So AI cannot replace in at least 10 years, I can assure you on that. Okay.
Sir,
Yes.
uh, after the macro placement, like we generally add a routing blockage, M1 routing blockage over the macro.
Right.
So why do we do that actually?
Okay. See, first of all, we need to understand what is a macro. Okay, maybe I have the image here also, right? So inside this macro, what we are having, we have some set of standard cells only, right? Standard cells and those routing information. Am I right?
Yeah.
Correct. So we inside this guy, this macro is developed by one more PNR engineer only. So he might use the M4 layers. Okay, M1 to M4 he might use. So we want to block those on top of the macro. Otherwise, if we not block, what will be happen? So our tool, our PNR tool will use. Okay, it want to route from here to here. It want to route with M4. Okay, if I not add blockages, but if you run it in a flat, okay, run it in a flat, there is a, you can see so many DRCs, or you can see the shots also, because inside the macro you're using M4, outside also you're using M4. So there will be a chance of getting shots, right, or DRCs. So that's why we can add the blockage on the macro till M4. Okay, because internally
so
they have used it.
Okay, so it can be M1, M2. Number of the layers might have been used inside the macro. That much routing blockages we need to add over the macro.
Exactly, right. Any other questions? Yeah, you can ask some advanced questions also. It is okay. Okay.
Yeah, Vishnu, any questions? Vivek, any questions? Vikrant, Vijay, Sushma, Sai, Ravindra. Yeah.
Sir,
Yes, guys. Yeah.
sir, these macros will follow the Cytros, sir.
Inside you're asking, or like how it will be?
Inside, sir.
Inside whenever they're placing the standard cell, right? So it will follow. But what will be happen this macro site row? So if you see, right, in your designs, sometimes it will not the follow the site row. Okay, you might see if you zoom in, the site row might be here, but it is not aligned properly. Like, so see here it is, right, like this. So that is okay in a macros case, but in a standard case it is not okay. So why it is okay, I will tell. Okay, so inside the this one there is some boundary. Okay, so your macro to inside the macro also you should be like this only, right? So there will be some boundary like here. So inside also you should have some boundary, and they will reserve some space for routing tracks. Okay, so if there is no cell placing here, what if there is a, for example, so this is my row, assume it is a macro. Okay, I have multiple rows like this. So this is my macro. So if it is a standard cell, if it is placed like this, it is legal. If the standard cell placing like this, na, it is illegal. But in macros case, if I can place like this, okay, this is a macro, right? So it is a legal only. So what I can do here, no cell is going to sit. Okay, I have ports here. I have ports here. So if it is a here like this, so there is no cell going to sit. Is it legal, and is it advantage or disadvantage? If you want to comment. So it is some kind of advantage only, because no other standard cell will sit here, right, in this area. So it will sit here only. So this area you will use for the routing resources. Okay, routing purpose you can use. Why this area will come, I'll tell. Okay, so what will be happen inside that, they have used all this, so they want to preserve some space. Okay, they want to preserve some space after the standard cell. So that's why they will add some extra margin. So that is okay for us. So sometimes what we will do, we will fill this area with the keep out margin, so to just some other legality violations, right, fake legality violations. I know, as engineer I know, but mission, if you involve into AI, it will consider it as a legal issue. Okay, but if you involve the engineer, it is a not illegal, it is a legal. Okay, if you involve AI, it is a illegal, it will consider it illegal. Okay, if you see as a human, it is a legal, because since it is a hard macro. So what I can do, I can add the keep out margin. If I cannot add also, it is fine. Okay, that is a space especially we will reserve for the routing tracks. Okay, so that's why it is not mandatory, but alignment of track is mandatory. Alignment of site row is not mandatory. Alignment of track is mandatory. Okay, it should be aligned to the track.
Sir,
Whatever the yes.
Sir, as VDD and VSS will travel on the same site runner, sir, how it will get, sir, this macro?
No, how why it will get. So okay, in this image you're asking.
Yes, sir.
No, actually I just drawn it for example purpose. Ideally if you take, so it is have multiple site rows, and anyhow it won't get power from this follow pin. Okay, if you observe clearly, we will cut the rows here around the macros, will cut the rows. Okay, so we will draw the power stripe. Power stripe will connect to the power pin. Okay, so macro power pin, so that power pin, it will supply the power inside the macro. So not, it won't get from the follow pins. We will cut the follow pins, we'll cut the site rows there around the macro. So if you have the access to the tool, just zoom in and see around the macro, you might cutting the site rows. Okay, so there is no this follow pin.
Okay.
You
Okay, sir.
observed it, right? Anyone has observed? Maybe you can confirm. Just same to this guy, like. Okay, so just you have the access now. Just zoom in and see. Surround the macros. We don't have any the follow pin and all. Okay.
Okay. Thank you, sir.
Yeah, good questions, good questions. Yeah, utilize that time. Okay, I just given a time, right? So you can utilize this time for your clearing your doubts also. It is very good, right? So I was happy to clear the doubts. Okay.
Any other doubt? Ajay, Arun, Asom, Ashutosh, Prithvi, Bhanu, Faisal Ali, Gopi, Harsha, Kiran, Naveen. Okay. So we are ending this meeting. Anyone have
Sir,
a
Yeah.
like
you
course
tell
like
that
what?
we are using non-adapt. We are not using non-adaptive technique only. We are using mixed and adapt technique. But here have a
Ha.
channel space between all in placement.
Okay. In the this one, right? You were talking partitioning. Am I right?
Types of partition.
Okay. See, that's a requirement. Okay. That is my requirement. See, I want to put some glue logic between, glue logic means extra logic between 3 and 4. So then I need some space, right? Channel space. Okay. So if I don't want, I can abort it. Either I want to, if I want to use the channel, then only I will go with this method. Okay. If I don't want, I can go with this method only. But nowadays we are utilizing this effectively. Okay, these channels we are utilizing effectively. So majorly from top level, right? So after some time, after the guy done the PNR, we want to add some extra logic, right? So I cannot go and ask that guy, okay, give some space in your block 3. I want to add some 100 cells. It's not working nowadays. So that's why we are going with the mixed. So we have some 5 minutes.
Open the placement diagram.
Yeah, sure. Placement image, right? Yeah,
Yes, sir.
opened. Huh. This one or
Yes, sir.
yeah.
In between, I have a basic doubt, sir. In between this not, sir. This, sir. In
Macros.
between some circles, red color circle, green color, no. We have drawn.
This one, huh?
Between this one also, in diagram.
Okay, here. You can tell where the top left like that.
Yes, sir. Down of the micro cells, sir. Green color you circle with red color, sir.
This one?
Between the micro,
Huh.
yes, sir. That area. What is that area, sir?
You not listened it. Actually, there is a one query someone has asked. So what is a magnet placement? I told. So first iteration of my floor plan. So this is my pink macro, some X logic. Okay. So this is the audio logic, you can say. So this is the audio macro. The logic is sitting here. Okay. If what is a magnet placement is asking, then I told. So if I want, if because of this, if I want to pull this near to this one, I can give this command magnet placement. I can give this macro as a magnet object, and I can give cell name. So it will move from here to here in the next place opt command or incremental place opt. You got it?
Okay, then
These
so
are
should we end the meeting?
all also cells, sir.
Sorry.
These all are also cells only, sir.
This all these this like dots like that you're seeing color.
Yes, sir.
These
Yes,
are
sir.
cells
Yes,
only.
sir. Okay. Thank you.
Yeah. So
So
why it
anyone?
is I taking this one only, because it belongs to this logic. That's why I was picking. Yeah. Take over, Ranjit. Your Rajat. Any queries,
Anyone
guys?
have any other doubt? So should we end the meeting?
Sir,
Yeah, Vishnu.
actually, I want to know, like, I would like to know how to give the weight values when we are giving the path group command. After placement, there is if there is any violations,
Okay,
then
right.
we can.
See, right. So based on the slack value, we can start giving the weight. Okay. For example, I have the 100 paths. Okay. So top 10 paths violating with 50 PS. Okay. From 20 to 30, it is violating with 10 PS. So top 10 paths, I can give more weight. Right. It's a preference. So slack is more, then you can give more weightage. So then it will take high priority, right, while placing. See,
Okay, so
group
based
path,
on
you
the
have to
slack
give.
values, we have to give the weight, right? Or is
Exactly,
there any
exactly.
other deciding factor?
See, based on the slack one thing, and for example, same endpoint was there, it meant repeating multiple times. Okay, so only one endpoint. Okay, you can see start points was different. 100 start point, one endpoint. So in this case also, you can give the high weightage, even though slack was less.
Okay.
I told two. One is the slack, and other is the more violating paths. Because if you fix this, all 100 will fix, right? Am I right?
Yes. Yes.
So
Yes.
there the engineer will involve, right? So that is what analysis, power of analysis. So if you do analysis, then you can fix in a one iteration. Otherwise, people will fix, start fixing only one. For 100, they will use 100 different commands. Okay. If you found the common point or valid point, then you can fix in a single go. I think we have left with 1 minute.
So we
So
can
if anyone
use
have any
bottleneck
doubt,
analysis, right?
Yeah, we can extend if you people have doubts also. It is okay for me, Rajat.
yeah, we can extend, but we will take the like complete course class. So if you want to
Huh.
register for the class, you can WhatsApp me. I will tell you the details and all. We will discuss it, and then we will. You should go for the complete course, right? Okay.
Yes, exactly. Yeah.
Okay, fine. Thank you, guys. Thank you so much. Thank you, sir. Thank you so much.
Yeah, no problem. Yeah. Thank you,
Thank you,
guys.
sir.
Have a great weekend. Yeah. Thank you.
Thank you, sir.